Welcome back. At this point, we are ready to take a fairly significant step forward. We're going to begin a new unit where we look at a linear elliptic PDE, but with a vector variable in 3 dimensions. And the model problem for this is elasticity. Specifically, we're going to look at linearized elasticity. Okay, because there are some technical issues, well, not just technical issues, but it turns out that nonlinear elasticity is not necessarily elliptic. Okay, so we're doing linearized elasticity. Okay, so we begin now with a linear elliptic PDE. In 3 dimensions. For a vector variable. Okay, and the model, like I said, is linearized elasticity in 3D. Okay, I'm going to start by writing out the strong form of the problem. So, the setting is one of 3D again, so we have our basis, our 3-dimensional basis set. Okay, we have our domain. We have, let me just draw the position vector of some point here. Okay, that point is x. Okay, so maybe I should write it at the point. Okay, this is x. Okay, so that's the position vector of x. Our body, as before, will again be denoted omega. And okay, let me now start out by setting up the problem. Okay, let me first state what data we have. We're given some data. Now remember, we're doing a vector problem, so all the data actually are vectors. Okay, vectors or tensors, in fact. Okay, so what are the data we have? We are given a vector set of vectors, and allow me to put the G as a superscript here. Okay, unlike the subscript that we were doing earlier, because I need to use a subscript to denote coordinates. Okay, so that little I there signifies our spatial dimensions, right? Okay, so we're given this as part of our data. Given UG sub I, we're also given what I'm going to denote as T bar sub I. Okay, we're given F sub I. Okay, these are all data. And right here, parenthetically, what I'm going to say is that what this really means is that U, G, T bar, F bar, now using direct notation, all belong to R3. Okay, so truly all I'm saying is that those data that I just spoke about are all vector data. Okay, so when I use Back here I've used coordinate notation, and back here I've used direct notation. Okay, so these are the data we have. Furthermore, we are given a constitutive relation we're given a constitutive relation which I'm going to write first in coordinate notation. Okay, the constitutive relation we are given is for the stress, a quantity that we call the stress. Okay, that will be denoted by sigma. It is a tensor, so it has, in coordinate notation, it has units. It has it has two indices, I and j. Okay, I'm going to put down here stress. Okay, the stress is given to us as through a tensor constitutive relation as equal to Cij KL epsilon KL. Okay, and what we have out here is the strain. Okay, I'll just state here that because we're doing linearized elasticity, the strain here, I'll write it out actually, the strain here is what we call the infinitesimal strain. Okay, infinitesimal strain. Okay, sometimes people like to specify that the stress that we're using here is the Cauchy stress, but it turns out that if you're doing linearized elasticity and infinitesimal strain, there is only the Cauchy stress, there's nothing else. Okay, this quantity here is what is called the elasticity tensor. Okay, it's a fourth order tensor, and it is what we call the elasticity tensor. Okay, now all of this, I'm not going to write it, but since I'm using indices, this is coordinate notation. Direct notation for the same thing, which I'll write in parentheses like I did above. Direct notation would be sigma, that's a tensor, and like I said once before, I'm using an underbar for tensors and vectors, we just distinguish them by context. Okay, sigma in direct notation is C, the elasticity tensor. Okay, and the fact that two indices are being contracted out here, K and L with K and L, is represented by a colon or two dots. Okay, just think of it as a generalization of a dot product. Right? That symbol is sometimes called a contraction symbol. Okay, and epsilon, right, in direct notation also. Okay, so let me just state here that that symbol is sometimes called it's sometimes called a contraction. I suppose the idea comes from the fact that you're taking a second order tensor, and which is epsilon. So the stress and the strain are second order tensors, right? And you're taking a second order tensor, which is the strain, and sort of contracting it down to a different second order tensor, or alternatively taking the fourth order elasticity tensor and getting rid of two of its indices, and thereby you're contracting down its the order of the resultant tensor. Okay, so that's the contraction symbol. All right, so we have all these things here. So this is the constitutive relation. Okay, we need more.